Okay, we're on to part 2 of activity 12-2 on the birth weights. So in this video, we'll do a few more parts of the activity. If you remember in the first part of this activity, we reviewed the idea of calculating proportions in a standard normal distribution using the table, and then we got an introduction to using it using technology to answer the same kinds of questions. All right, we're going to do the same thing here, but we're going to answer a couple of slightly more complicated questions. Okay, or maybe complicated is not the right word, but we have to do a little bit of thinking about how we're using our table. Okay, and how we're thinking about things. Right, so we got the same scenario. Okay, where the birth weights of babies are modeled by the normal distribution. Okay, so we got our curve. With mean 3,300 grams and a standard deviation of 570 grams. So we got that picture in our head. And then the two questions we're going to pursue in this video are what proportion of babies does the normal distribution predict as weighing greater than 10 pounds, okay, instead of less than, all right, so that's a change. And then we want to determine the probability that a randomly selected baby weighs between 3,000 and 4,000 grams at birth. All right, so we're going to answer both those questions using Table 2, by hand, in other words, and then we'll also answer them using technology, check our answer using technology, and then we'll also compare that at the end with the actual data, okay? So let's go after that first one, that first question. So switching cameras. I've got a kind of a nice clean picture of my distribution, and we want to talk about the proportion of babies that the normal distribution predicts as weighing greater than 10 pounds or 4,536 grams. Okay. All right. So I want to first thing I want to do is graph that, or not graph it, but indicate that on my in my picture. Right. So 4536. It's going to be somewhere up here. Again, I'm not sure where. And we're talking about weights greater than that. Okay? And so that's that little tiny area there is what we're talking about, right? Most babies weigh less than 10 pounds, right? But there's a small fraction that weighs greater than 4536. So this area represents the proportion of babies that weigh more than 4,536 grams, right? Okay, so the plan is the same, all right? We can find out how extreme that weight is by calculating the z-score, okay? But then remember what the z-score tells us, right? The z-score always gives us area to the left. I should say not the z-score, I should say the table. The table always gives us area below a particular z-score, right? And we want the area above. So I want to think about, I won't tell you the answer yet, but I want you to think about how we find the area above, all right? But let's find the z-score, okay? Our z-score is our observation minus our mean divided by our standard deviation. So it's going to be 4536 minus our mean, which is 3,300, over our standard deviation of 570. Okay, and I work that out. It comes out to about 2.16842. Okay. All right, remember what that means, right? So it's positive. That means our observation is above the mean. And it's 2.17 standard deviations above the mean. Again, a pretty extreme observation, right? Okay, so let's go to Table 2. All right, and Table 2 always gives us area to the left. So if I look at, let's see, I'm going to look up 2.17. I'm on my second page, 2.1, 0, 1, 2, 3, 4, 5, oops, sorry, 6, 7, 0.9850. That's the area to the left, right? So all this area, back to my camera, all this area back here is 0.9850. Right? All this area back here. So what does that leave for up here? We know that 100% of our observations are under the curve, so the probability of getting a weight bigger than 4536 is the same, or at least approximately the same, as the probability of getting a z-score bigger than 2.17, and that's going to be 1 minus 0.9850, right? 100% minus 98.5%. So that's going to leave us with 1.5%, okay, or 0.015. Okay, so about 1.5% of babies have a birth weight greater than 10 pounds. All right, make sense? Okay. All right, so on to one more. All right. We want to find the probability that a birth weight is between 3,000 and 4,000 grams, right? So that was our other question we wanted to pursue in this video, right? So there's our notation. I want to find the proportion of babies whose weight is between 3,000 and 4,000 grams, or alternatively, that's saying that if you choose a baby at random, what's the probability that that baby will be between 3,000 and 4,000 grams? All right, so let's shade the approximate area. Okay, so it's going to be almost halfway in between here. So there's 3,000, and then 4,000's up here. Okay, and that's this area, right? Or said differently, this area relative to the total area under the curve is the proportion. Right? Okay, again, you can see the challenge, right? That table 2 gives us area to the left. We want the area between these two values. Okay? All right, so let's do a little bit of work. Okay, z-scores will be helpful for us. All right, so let's find the z-score for 3,000. And then let's find the z-score for 4,000. Okay, and here's the big picture. Okay, I can find the area to the left of 3,000, and I can find the area to the left of 4,000 under the curve. I want the area in between, so can you see it's going to be the difference of those two? Right, so if I have the area from 4,000 on down, it's going to include all of this. The area from 3,000 on down is going to include this, and so if I subtract those two values, I'm going to get what's left in between. Okay, so it's just a more sophisticated way of using table 2. It'll work great for us. Okay, so for 3,000, let's find the z-score. So z is going to be 3,000 minus 3,300 over 570, and that comes out to be about 0.53. Negative 0.53. All right, rounded at the 100th point. Okay, again, indicating that it's about half a standard deviation below the mean. All right, and if I want to find the likelihood of getting a baby weight less than 3,000, that's about the same as the probability of getting a z-score less than negative 0.53. Look it up on table 2, and you'll get about 0.2981. Please check that. All right. All right. For 4,000, z-score is 4,000 minus 3,300 over 570. Okay. An observation of 4,000 is more than a standard deviation above the mean. How far above the mean? Well, figure it out. 4,000 minus 3,300 is 700 over 570. That comes out to be about 1.23 standard deviations above the mean. Again, rounded at the 100th point. Okay, so then the probability of getting a weight less than 4,000 is approximately equal to the probability of getting a z-score less than 1.23. Reading off table 2 as always, I get 0.8907. Okay, now as I said, we don't really want the area to the left of 3,000 or the area to the left of 4,000. What we want is the area between 3,000 and 4,000, and we get that by subtracting these two values, right? So the probability of getting a birth weight between 3,000 and 4,000, that's the same as the probability, or at least approximately the same as the probability of getting a z-score between negative 0.53 and 1.23. And that's going to be approximately the same as 0.8907 minus 0.2981. One more time, that's a big idea, right? I know this area down here is 0.2981, and I know that the whole area back is 0.8907. I want this area, so I'm going to subtract those two. All right, so when I do that, I get, again, check me, 0.5926. Okay, so about 59% of babies weigh between 3,000 and 4,000 grams at birth. Okay, all right. Let's check this using our online applet, and then we'll compare this to what actually happens. Okay, see how well it reflects reality. Okay, so if you didn't watch the other the previous video, let's just do this from scratch again. So on our home page on Canvas, I'm going to scroll down. I'm going to go to my Rossman Chance applet web page. Open it in a new window. I want the normal probability calculator. Okay. My variable is going to be, I'll use W for birth weights. Okay. My mean is 3,300. Standard deviation is 570. And again, no picture right now until I scale to fit, and then I get the picture that I just drew on. Let's first check our weight for, or our probabilities for babies weighing more than 10 pounds. So I want a greater than 4536. Okay, and you can see that that again, a baby weight of greater than 4536 grams is a very small likelihood, right? And that actual probability is 1.5%, which we calculated by hand a little bit ago, right? Okay. All right. So there's that answer quickly, and now let's do 3,000 to 4,000. Now I want to find the proportion of baby weights that are greater than 3,000 and less than 4,000. So you got to be careful of your notation here, right? So I want my weight to be greater than 3,000. Okay, so that's my picture there, and I also want the area less than 4,000. Okay, and here it is. It tells us the probability between those two values, between 3,000 and 4,000, is 0.5910. That compares very favorably to our 0.5926, right? This is a better answer. It's more exact. Okay, the 0.5. So 59.1% of all babies are between 3,000 and 4,000 pounds. Okay? All right. Okay, one more thing, last thing, I just want to check how well this reflects reality. Okay, so we have some actual data from 2004, and the question is, does the normal model seem to do a good job of predicting the actual events, right? So we had this normal distribution, and all we were given, right, all we were given was the mean and the standard deviation, and the fact that the normal model fit our situation pretty well. Okay, so now I just want to check, does this work? Okay, how well does it reflect reality? Okay, so we've got the data, low birth weight babies, total births, 3,000 to 4,000 gram babies, we can just do that calculation, right? So just very quickly, let me switch back to my picture and zoom in so we can see our calculator. All right, I'm just going to calculate those proportions, right? So the total number of low birth weights was 331,000, let me clear, 331,772. Total number of babies was 4,112,052. Okay, and 8% of babies were low birth weight, right, back then. All right, that fraction, okay, the low birth weight babies, that's the number that we came up with in our previous activity, or sorry, the previous video, right? So we calculated that 8% using the normal distribution in our previous video, right? Okay, so that fits very well. Okay, and now we just calculated the 3,000 to 4,000 gram babies, that proportion. So let's check that data. All right, so it says 2,697,819 out of that 4,112,052 babies in 2004 were between 3,000 and 4,000 grams. Okay, remember the number we came up with just a moment ago? We got about 59%. Let's see how this works out. Came out to be about 66%. So not perfect. Just want to make sure I entered everything right there. Yep, not perfect, but still not bad either.